Hello, we're back again. Our next speaker really needs no introduction. He's been moderating for most of today, but we'll go through the formality, and it's my pleasure to introduce David Lahrman. David is the Vice President of Business Development here at LSP Technologies. David has over 25 years of materials process engineering, and he serves as the primary point of contact for our new customers that are seeking a solution to their metal fatigue challenges. David's been with LSP Technology since 1999, and he brings with him experience as a research scientist at Battelle and as a lead engineer at GE Aircraft Engines. So David, welcome to the podium.
Thank you, Eric. Appreciate that. So I'm going to talk a little bit about just the application of laser peening and really more about the path to production. So a little bit about the outline, really talk about laser peening and the benefits, which for the most part we've really covered. I just want to be able to tie it back to some of the earlier presentations that we've had today to kind of keep things linked together. And then we'll talk about the processing application, a bit about the design engineering, give you an example, part of which you've really kind of seen from Stan Bovid's presentation earlier today. And then just talk about the implementation and what it really means relative to components that are in service today and what the future may actually look like. I'll start out with just kind of summarizing some of the benefits. I think most of us are already aware of this. This has really kind of been covered through the day, but we're really using residual stresses to improve the fatigue life or the fatigue resistance of metallic components. And it has an impact on a different variety of types of issues that are encountered in metallic materials. We can use it to resist crack initiation. There's information out there to support that. Fretting fatigue is another area as part of that. And what I really want to be able to demonstrate and show today is that the part that's really becoming important for the implementation of laser peening or any engineered residual stress is really our ability to model and demonstrate the benefit of a residual stress and then compare some of those profiles and opportunities for improving fatigue resistance that we didn't have years ago. Some of the basic data we've seen today, Michael Couture has presented some of these view graphs, and my intent here is not to actually walk through the details of those, but really to say that there's a lot of data that's been generated. This one, for example, provides a bit of an overview of the fatigue life or fatigue strength, depending on how you actually want to take advantage of the compressive residual stresses in the part. You can either improve the life of a component so that it lasts longer, or you can actually improve it so that it maybe actually has a higher capability. Michael also presented this view graph earlier, talking about stress corrosion cracking and the ability to improve or the capability of various materials. And in this particular case, it's a stainless steel. So again, it's the data that's behind what we are generating, and most of us are generating this kind of data to help us along. Another area that's a benefit to the community is certainly fretting fatigue resistance. There's been some work there. They're very well-controlled test data to demonstrate the ability to mitigate the effects of the shear cracks that are generated in a fretting fatigue scenario. Again, these are the kinds of data that are important for helping to implement laser peening and engineered residual stresses to understand the value of what's being applied. And maybe a graph that's maybe more typical of what some of our design engineers are used to seeing is this type of what they call stress strain or a life cycle SN curve, stress life curve. And it's a typical curve that are used by design engineers to size components that go into a variety of different opportunities. We're showing here, for example, the data that was generated on 7050. Which is a typical aluminum alloy that's used in wing spars, for example, on aircraft. Earlier today, Jeff talked about the application of residual stresses in one of the earlier applications, this being on the F101 turbine fan blade. And one of the things I want to point out here is that the prior applications really occurred without really the engineering portion of it being able to model it or demonstrate what the modeling scenario might look like. The approach was very Edisonian. There were a couple different tries in terms of trying to figure that out. In this particular case, was the processing conditions that were used, and the patch were identified fairly quickly. And I think Alan pointed out earlier today, it was kind of a lucky lottery hit. But I think in terms of what's being applied and done to that particular component, if we were to use the engineering approach that we'll talk a little bit about, we might actually look at it differently and being able to provide the same solution that may be more effective. Another one, in terms of Pilger dyes, again, this was very Edisonian in terms of the approach. Several different processing conditions and patterns were applied to the dyes. And really the only way to demonstrate the benefit of that residual stress in these dyes was actually to test the dyes actually making product. And once the residual stress profile and the pattern that was applied to the part was determined and identified as the one that worked, the customer in this particular case was actually able to produce 3 times more tubing than they were actually able to do without laser peening. And from that perspective, when you start looking at what the advantage is, the cost of this dye is not the expensive part. The fact that you can now triple the life of this dye and not have to worry about disassembling the Pilger die stack, which can take several days in order to disassemble and reassemble it to make material or product, the customer in this case now has eliminated basically 2 maintenance cycles. But again, this was all very Edisonian, even up through the mid-2000s timeframe. What I want to walk through now is kind of the discussions that we have with our customers in order to help them understand the benefit of laser peening. And what we're seeing here that I've actually highlighted is a new element in terms of that process to help the customer walk through basically acquiring and implementing laser peening or engineered surface stresses in components. We've talked a bit about design analysis in terms of collecting some of the data. We've kind of heard that woven through some of the talks today. And that's really kind of understanding the issues behind it. The process about application verification, which is in the middle box, is something that I won't really touch on because that particular part has been in play since the beginning. When they started doing, for example, the F101 blade, there were a lot of tests that were run, component fatigue tests that were run to validate the benefit of residual stresses. And then the production launch, once you finally have developed that process condition, you lock down that process so that you can use that same processing condition and pattern over and over again, and you have verified it with your previous effort to validate it. And then obviously it's then supporting the production so that you can purchase the process on the parts, and the customer who ultimately receives the laser peen component realizes they're going to have the same benefit in the part. So where does it all start? And I'm just going to walk through kind of that experience that we have with our customers today. Well, generally, when we sit down and talk with our customers, the conversation really starts out really trying to understand what they're encountering or what they're trying to solve. They may have a lot of information about the part. That collection of the facts is an important part. They may have a lot of information about the failure location. They have done their failure analysis, so they've determined the cause, which may actually include a lot of statistical population. Or to back up a little bit further, the only thing they may actually have is an analytical model, a finite element model that they've conducted themselves that kind of shows the high stress points in their part and their anxiety about potential failure in those high stress locations that are impacting at the surface. Once you've kind of begun to collect all of the data and understanding the issue that's associated with it, it's really now defining and understanding what you really want to get to. So you got to evaluate the component. And so in that process of doing that, it's looking at things like the finite element model, also working with understanding the vibratory modes, how that part works, so you understand the stress distribution in the part, and also being able to model that part. So once you've determined what you're trying to accomplish by determining the final outcome, what kind of a life benefit are you looking for? What are you trying to mitigate? then you start to trying to really define the parameters by which you're going to laser peen that part to really provide the benefit. And that's where what we call design engineering really comes into play, or the modeling portion of it. And earlier today, Stan Bove had talked about some of the modeling he was doing and has been doing in terms of forming parts. Well, that modeling capability isn't all that much different in terms of what we're doing in terms of applying the process on the surface of parts for improving fatigue resistance. So it's the modeling and simulation effort that has become important. And what you see in some of these images here are really the evaluation of applying residual stresses in the surfaces of a part, so you can understand where the compensating tensile stresses are going to go and how those compensating tensile stresses are then interacting with the various stress states in the part itself that have been conducted in the finite element model. From that, you really begin to determine the laser peening conditions that you're going to use to provide that life benefit. And the design engineering, I think, is really significantly important because, as I talked about earlier, we want to eliminate the Edisonian approach. We want an accurate implementation of the process, but we also want to reduce the time of implementation, and being able to shrink that time down from what was a few years of effort to make that happen, now down to less than a year that Jeff had mentioned in his talk is an important element to be able to do, because we want to use these stresses, we want to apply them quickly, and we want to capture that return on our benefit. The other area that's significantly important, we have some very large structures today that we're laser peening. We had William Sims from Entergy talking about the application of engineered residual stresses to the reactor head portion of the part to improve fatigue life. Those structures are large enough that actually doing a component fatigue test on those is difficult to do, and there are not very many of them. There are limited quantity of those types of components, so being able to conduct a test on that is difficult. So when I say difficult to conduct validation tests, you have to be mindful of the kinds of information you have, the size of the structure that you're working with, in order to be able to validate that. And I think probably having some modeling capability that in the early days of really working through the data, even for the reactor heads, would have been very helpful in terms of pushing and accelerating the implementation of laser peening. So component simulation really relies on, I think, the coupon data to support it, because that's the information that goes in to help the modeling capability. Obviously, you can do the modeling and simulation to determine the profile, but it's also the data that actually gives you the confidence that your model is actually predicting correctly. And then when you combine that with the component finite element analysis, you can work those two together from the modeling simulation and from the finite element analysis to say, okay, have we really driven home a processing condition that will benefit the part, provide the life that we're looking for, and also be a cost-effective process. The other aspects of design engineering that we have that we can actually pull in to help us out with is obviously a lot of data has been generated, as I had mentioned earlier. We generally know kind of really where we're starting with in terms of specific alloy types, what types of power densities we're going to use to process those with. These are kind of the ranges that you will see in the data that we've been using. These are starting points. These are not absolutes. These ranges help to guide what kind of power density you're going to use, but obviously the configuration and geometry of the part are going to play a very important role in determining what power density and process condition you're going to use. The other part that comes into play is what type of coverage, and we've talked about those as well, in terms of the placement of the spots or the pattern in order to cover the area to be processed. I think it was Stan who was showing 3 different versions of that. Michael may have covered that as well, at least 3 different types of patterns. Each has some unique capabilities in terms of what that profile will look like once you've used a particular pattern on a part. And again, we can model to a certain point and simulate what we're trying to accomplish. And that profile that comes out of that will help us to understand what the overall stress state looks like when we model that. I thought I'd walk through an early example that we had started with to kind of give you an idea of the benefits and value of modeling. Stan showed some of this in his discussion earlier today relative to the application of peen forming. In this particular case on this Wankel crankshaft, there were 3 different locations in this particular part that the customer was encountering fatigue and wanted to improve fatigue resistance. And this is one of the early opportunities to really sit down and start looking at using a modeling and simulation model that Stan put together to kind of look at that. You can see highlighted in the upper left-hand corner, these are the areas marked in red that the customer was looking to provide laser peening or have laser peening applied to the surface of the part to improve fatigue resistance. One of the models that Stan pulled together to simulate what that profile would look in the part is in the lower left-hand corner. You can see what that profile looks like. In the process of actually now laser peening those parts, what we encountered was, and hadn't really spent time looking at, was now we actually had residual stresses built into the part, but the axis of that shaft was no longer concentric. And so that presented an issue. We've improved the life of the component, but now we made it so that at this point, it wasn't usable to be able to put it back into service. Again, with the modeling element, Stan was able to go back and say, okay, how do I correct that shape? Much like he was talking about earlier today, by being able to add in and evaluate it analytically with a modeling and simulation capability, there were a couple locations that Stan identified to be able to add that stress in certain locations to straighten the shaft. That proved actually highly successful. And you can see from the model here in the lower left-hand corner, the stress distribution in the part is a result of the additional stresses in the fillet regions between the asymmetric lobe and what occurred. In the process of doing that, what we ended up doing is providing shafts that actually met the concentricity requirement for that particular shaft. And so the point being here, it's really to make sure when we start looking at the application of stresses to mitigate a particular fatigue issue, you really need to understand what those stresses are doing, where they're going, the impact on the configuration of the component. And so it's the engineering portion of this that helps us to solve this much quicker. This just shows a comparison between the before and after correcting the shape of the Wankel shaft. Really just showing what the profile looks like and what the stress distribution in the part would look like. Another one that Michael briefly talked about was this arresting hook. And really the application of stresses is in the shaft where the shoe actually bolts into. There's a fillet radius in here that's much shown here. Again, the application of the residual stresses was an engineered element to make sure that we kept the stresses that were encountered in that particular fillet radius below a certain value so that we could have multiple arresting by the aircraft that were used. And as Michael had indicated in the graph, the prediction of life certainly improved the capability of that part. But again, it's making sure you really understand the application of the residual stresses and modeling that component with a finite element model analysis to really understand the impact between the operational loads and the stresses that you've imparted. So laser peening implementation. A lot of the work that's been done to date really has been on in-service components. We've already talked about some of those, the F101 turbine airfoil, the Pilger dies, the reactor head that William talked about today. Those are all in-service components where we're now trying to use their engineered residual stress to prolong the life of that component. So we're using it in a way to help parts that are already designed without changing the design of the part, but making sure we understand the distribution of the residual stresses in that part. The part that really becomes important moving forward in the future is really using the engineered residual stresses in a way that helps me to increase the flexibility or durability of a component while achieving other objectives that were not maybe achieved if I were doing it on an in-service component. Can I use laser peening, for example, to replace maybe an expensive premium alloy? Can I use engineered residual stresses to increase the flexibility and durability of the component while maintaining some level of weight efficiency or lighter materials? Because in the aircraft industry, that's an important part. But I also think that's an important part in the maritime industry, in the transportation industry. So being able to use and leverage engineered stresses and using our design engineering capabilities is an important element to moving it into the future. This is just a list of some of the potential applications. Some of these are already in play. Danny Georgiadis just talked about in the maritime industry. This is a shaft that's used in a ship. And so there are certain locations on that shaft where you can improve the fatigue resistance and durability on that. These shafts come in at a specific frequency to make sure that they don't fail in service and that they provide the propulsion that's necessary, especially and critically important, as Danny had indicated, on single shaft ships. Areas that can take advantage of it that we haven't really talked about much, but we have customers approaching us is in the medical industry. And here I'm showing a hip implant. There are locations in here where you get failures because of the way these parts bend while they're implanted in the body. Obviously, the surgeon who's putting these in the body would prefer to do this once for an individual, and that part will then last in the life of the individual. Being able to provide engineered surface residual stresses in there is one way to approach that. The other area is obviously in some of the tools that are associated with making or conducting surgery. That's another area that's of importance. We've already kind of generally talked about transportation, but things like crankshafts, I think, not recalling exactly who today had talked about crankshafts, but that's an area, I think it was Michael Coutura. So being able to engineer residual stresses on crankshafts, which is a component that's been around for well over 100 years, is an important capability of extending that. So if you're going to design a new engine to go in a locomotive, for example, being able to apply engineering residual stresses to that part to remove some of the weight so that becomes a more efficient system is a way to begin to look at those. So surface enhancement is also about the return on investment. So obviously we're making an investment by applying that to the surface of a part to extend that. What we want to do is basically reduce things like the total life cycle cost, or replacement of parts, because if a part wore out due to fatigue, I've got to replace that with a new part to put the product back into service. Reduce maintenance cost or inspection cost, as we had seen earlier today. Those are certainly important parts. Eliminate or mitigate downtime, as I had talked about with the Pilger dies. And basically just the risk to system and personnel. So we're actually making sure that people are in a much safer environment, and we're making the world a safer place. The other part of it is also the surface enhancement increases part life. So we're taking advantage of that. System safety, system readiness, system durability, and effectiveness. And so in terms of understanding the return on investment, it's not just about the first cost. It's also about the whole picture cost of implementing that residual stress on the surface of the part. And if you go out and look at the website, there is information published out there, for example, on the cost savings associated with implementation of laser peening on the F-101. It's in about the $500 million range because of the savings associated with it. So the question we get often asked is, how much does it cost to do the surface enhancement? Well, I'll say less than the cost of the surface of the life of a part, but you got to pull in the rest of the cost associated with that product. And not just look at the first cost, but the overall life cycle cost of a part comes into play. The other question we get asked frequently is, how long is the service life extended? That can be anywhere from 2 to 5 times. That'll be a function of the design architecture of the part, the material of the part. So those will come into play in that prescription. So I just want to kind of come back a little bit to the graph that I had shown earlier that had basically the path to implementation, and really just focus in on the important part that's really coming and maturing that has to be imparted into this is our design engineering. And that's where I know LSPT are pushing that, but there is not just LSPT who's pushing and developing the modeling capability. There are others as well. We're learning along the way. There's work yet to do to make that happen. The more we can do that, the better we're going to be. I think even in the discussion we had with Ted Fecky, understanding just the value of being able to model it and then taking design credit for that is an important element. And the way to get there is through our design engineering and validation efforts. The rest of this is pretty much as we've already done before with the validation of the parts, launching and the ramp up and life cycle sustainment. So those are the pieces, or the piece that I wanted to point out today in the implementation of laser peening, is that the tools that we are designing and building today to mature are really critically important. So in summary, and I've already started that, the design engineering is important. It eliminates the Edisonian approach that we've used in the past. It leverages the finite element analysis and modeling and simulation to be able to evaluate the component, determine what's the best way to process it to achieve the benefit we're looking for. It also confirms the processing conditions. What are we going to use for processing conditions? What are the areas that need to be processed? More is not always best. So it's really about tailoring it to make sure you reach the right prescription to achieve what you want to in that part. The modeling also can be used to help support validation, because as we had talked about earlier, sometimes the components are so large that maybe the only way to really validate it is through modeling. And as I think Ted Fecky was pointing about in his presentation, being able to accept that validation and design credit associated with the parts is important. And then lastly, obviously driving the future of design of components is going to be the real important part. Maturing these models and our design engineering capability will help drive home the implementation of these engineered residual stresses to improve life of the component, or give us really the design flexibility that we did not have before. Thanks.
All right. Looks like we have some people in the chat asking some questions. Let me read those off to you. So the first question, David, is, do you see that modeling capability is more helpful in service applications or for future applications?
I actually seeing it being helpful for both. A lot of our work right now is that we've done with in-service applications. So being able to model a component that's being used today and really figuring out what that prescription is important, because we can actually narrow in what the prescription looks like. I think it's also important for reducing the amount of time for implementation. So instead of doing several iterations to get at the right process condition or the right process pattern, we can model that first and cut down the number of iterations, hopefully to 1 or 2, and then validate that through some validation testing on the part. Obviously, I think moving forward, to be able to do that with a real world component that we want to design for the future, that's going to be an important element to really help us leverage our ability to use and implement laser peening on our future components in a way that we can't right now on in-service components.
All right. And looks like they're okay with that answer. And then one other question about, when did LSPT first start relying on modeling the combined stresses?
So I think the Wankel crankshaft was one of those first ones that we started with. And I say we, it's really Stan. And I give Stan a lot of credit for pushing us along to do this. And he has the wherewithal and the desire to make that happen. That really occurred in about the 2014 timeframe. And since then, we've actually continued to build out and strengthen our modeling capabilities. So that's an ongoing effort.